Okay, so we are happy to have Bartul Mukhopadhyay with us, virtually, and he's going to talk about how to define things properly on a lattice.
Okay,
Bartul.
thank you, Sumit, for having me, and thank you all for coming to the seminar. So about a year back, I discussed this topic, and then later found out that something was not fully understood. So that resulted in some further development, which I wanted to talk about, which is the temper distribution theory on a lattice. Um, I tried to prepare the talk slightly differently than before so that it doesn't sound too repetitive. So let's see how it goes. Um, so it's going to be based on a paper I wrote in 2023 that was on string theory, string worldsheet theory, and now I'm going to talk about more on this Poincare invariant constructions. So let me begin with some motivations. Um, So if we take a classical theory, that classical equations cannot be valid all the way up to the zero length scale that we know because the classical description does not go is not valid all the way up to that scale. So there's going to be a minimum length scale beyond only after that theory is going to be valid. And if we have and therefore we write although we write a classical continuum model, it's not necessarily, that's not what we actually mean to be true realistically. In order to solve that model, we if we cannot solve it either exactly or perturbatively, we take the help of numerical recipes, and there we discretize, and basically we construct a discrete theory corresponding to that, where we replace the continuum derivative by a discrete derivative. This theory that we write, the discrete theory, is in the difference approximation, as we are replacing continuum derivative by a difference derivative, and also non-unique, because in the continuum limit, many more theories will go to the same theory. But as I mentioned, that this continuum model one could view is as a mathematical model rather than a realistic one, because realistically we know that it is not going to be valid all the way up to the zero length. And therefore one could imagine maybe there is another discrete model which describes it, which is different from the approximation that we considered. And this discrete model must be symmetric, though we don't know what it is. It should be symmetric because we see the symmetries in the continuum model. And if we take the scenarios realistically that the theory is defined in the continuum, I will refer to that as a continuum hypothesis. Okay, which means that the theory is fundamentally defined in the continuum. So this is all we understand very well, and but what we do not understand very well is the corresponding quantum version of that, which is what was Wilson defined earlier in 74 or something in the 70s. We are trying to define a quantum field theory in the continuum, and his view was to look at it as a critical behavior emerging from a lattice construction. So he brings in the idea from statistical physics, and here in the usual condensed matter scenario, we have microscopic physics, and then when the critical behavior emerges, it goes to a larger length scale. The behavior is visible at a larger length scale, and that behavior is to a large extent independent of what the microscopic theory was. So he mimics that mathematically and tries to construct write down a theory on the lattice scale. This lattice is like the microstructure of the quantum field theory, and the quantum field theory is supposed to emerge as a critical model from that. Now, this procedure going from here to here, taking the continuum limit, is an extremely non-trivial thing to do. There are two aspects of it. One is the universality, which means that you could write many lattice models, which are all supposed to give you the same critical model. And those must be guided a lot by symmetries. If you take arbitrary theory in the microscopic description, that's going to spoil this critical behavior. And also, after fixing the theory, the Bayer parameters must be tuned, and usually one takes the input from perturbation theory to fix the behavior of the Bayer parameters, to find this very finely tuned situation of having a critical behavior, which is going to become independent of the lattice structure. And that's how the continuum theory is defined. Now, the problem in finding this finely tuned critical behavior is that on the lattice, we do not have symmetries, and the symmetries are supposed to play a very important role in this. So if the symmetries are preserved, then it guarantees more that we find the critical behavior. Otherwise, it is not so guaranteed. It's a numerical experimentation that one has to do in order to do that, but there is no mathematical understanding of how it is happening. In this case also, we could take the same view as I did for the classical theory, that the continuum model or field theory is not going to be true all the way up to the zero length scale, because we do perform experiments only up to a particular length scale. And therefore, if we do not accept continuum hypothesis, we could probably write down a discrete model which will have the symmetries. And that will be another way of looking at it. And it's not clear whether this entire scenario here of finding critical behavior and the formulation in this case also should go in the same manner. But that's the possibility that I would like to think. Now, on this side, the standard practice of lattice quantum field theories, there are several issues that are relevant in this discussion, which I have tried to list some of them here. And the one is lattice artifacts, because we do not have symmetries. How to get rid of the artifacts and the critical behavior independent of that artifact must emerge. That is not very clear, and therefore it requires improvements, and those have been studied. When we write down the macroscopic theory on the lattice, there are fermion doubling problems and loss of chirality. These are just mathematical theorems that a naive age going to zero limit is not going to give you the continuum model, unlike in the classical equation and in the differential equation case that I mentioned in the previous slide. I will be talking a little bit more about this Feynman doubling problem later. A related aspect is supersymmetry. The supersymmetry is also very difficult to preserve, because you are not preserving symmetries on the lattice. You have to ensure that in the continuum limit supersymmetry emerges, and that's a very non-trivial thing to do, because bosons and fermions are latticized in different manners, and you need a lot of fine-tuning to make sure that the supersymmetry emerges in the continuum model, in the continuum limit. Now, the fact that the supersymmetry is very difficult to get in the continuum limit shows that this problem here of taking continuum limit is very difficult. If you had only bosons and fermions and you take continuum limit independently, you might get Poincare invariance, but the balance between bosons and fermions may not appear, may not be achieved, and that's what leads to fine tuning. In the context of string bits and ADS-CFT latticization of the worldsheet theory, this problem appears, and there also one has the same problem, because worldsheet theory is supposed to have this various symmetries, like local symmetries, and when you discretize it, what you usually do is to first fix the symmetry and then discretize. So the lattice theory basically forgets the symmetries that it had, and there is no compulsion to obey any consequences of that symmetries, and therefore in lattice calculation, the lattice artifact, there is no estimation even how much is the lattice artifact and how much is the actual result. This estimation cannot be done because there is no symmetry. So preserving symmetry is a very important thing in the context of worldsheet theory, yeah, and have a BRST formulation, even at the lattice level. Now, all this all quantum field theories are defined with a UV regulator, and no regulator preserves all symmetries, and therefore the regulator must be unphysical and must be lifted. That is the usual argument, and it's a fair argument. And if you apply this argument for the lattice, then you basically end up getting continuum hypothesis. So we have a technical formulation of quantum field theory where the regulator is unphysical, but when the regulator is a lattice regulator, then lifting the regulator means going to the continuum. So we commit to continuum hypothesis, whether we like it or not, we have to do that. So, and all the conventional existing framework like conventional QFT, which is the perturbative quantum field theory that we regularly use to do particle physics calculations, lattice and axiomatic theories, all of them take continuum hypothesis as granted. It is based on that hypothesis. If it's a conventional, if it's an axiomatic theory, then they also start with from the very beginning, they start with symmetries. Now the question, so this is somewhat a problematic situation here because we have a technical requirement of lifting an unphysical parameter. We didn't want to believe in continuum hypothesis, but we are led to do so, though there is no objective way of verifying that that hypothesis is right. This problem would take a different, shape if we had a cutoff that preserves all the symmetries. So the question is that if we have a cutoff that preserves all the symmetry, should we interpret that to be necessarily a physical parameter, a physical cutoff? So I'm going to talk about.
Can I have a quick question?
Yeah.
When you say symmetries, do you mean like real symmetries or also redundancies like gauge invariance?
Yeah, all of them, because gauge invariance, also we have developed experience about gauge invariance to make sense of the theory, right? We use gauge symmetries to make sense of the various observational things. So we know how to deal with gauge invariances. And gauge symmetry is non-trivial. That also happens in the worldsheet case because there are local symmetries. Those have non-trivial effects in the sense that in the sense of BRST, like when you fix the gauge and quantize, there is no a priori guarantee if you had fixed the gauge in a different way and quantized. So the two quantum theories must be equivalent. Without gauge symmetry, this condition will not appear. So without gauge symmetry, this is more restrictive in that sense. So that gauge symmetries also should be preserved on the lattice. I mean, whatever classical theory we have, we should maintain all the symmetries for the quantization. Now, let me briefly go through some of them I had gone through earlier, but let me briefly go through some whatever topic I'm going to discuss, a certain relevant development in the literature I would like to touch upon. So let me do that. So what happens is that you take the continuum theory, which is the classical theory, which has a continuum derivative, and you replace that by the difference derivative, with the hope that in the continuum limit, by the way, I will be using H as the lattice parameter, which is not the standard thing to do. A is the standard notation, but there are many slides that were written in H, so I couldn't change them quickly. I apologize for that. I will continue to use H as the lattice parameter, lattice spacing. So we hope that the theory written in terms of the difference operator will go back to the continuum theory when we take H going to zero limit. After doing all the calculations here, we are doing calculations only here in the middle with the difference operator. And Nielsen-Ninomiya theorem says that is precisely not true because at a finite H, you have fermion doublings and loss of chirality, and these properties will not be washed away when we take H going to zero limit. So, and this happens, one of the conditions of Nielsen-Ninomiya theorem is locality, which means that the derivative, there is a non-uniqueness of what you write as a discrete derivative. If you take the discrete derivative to a finite power of the difference operators, which means that the derivative operator is connecting a finite number of lattice sides together, then this theorem applies, but this is not true for non-local theories. So that's what Drell, Weinstein, Yankelovich tried in 76, writing down a non-local theory to get rid of the effects of Nielsen-Ninomiya theorem. And this is usually called slack derivative. And here, what you do is to take this psi p is the lattice field, you take the Fourier transformation, BH is the Brillouin zone, first Brillouin zone. And then they say that this derivative is such that applying on the Fourier mode on the lattice is going to give you the same result as in the continuum. Therefore, you get IK. But now if you Fourier inverse transform psi hat k and write that in the position space, then the derivative picks a PQ structure that's non-local, because for every value of P, all values of Q will contribute as it is given by this expression. So it's a non-local derivative, and it is a dispersion law that comes from this derivative, which is exactly the continuum. It gets rid of the Fermion doubling problem and chirality problem. However, there is no Fermion doubling or chirality problem, but there is another problem, the problem of symmetries. And they show in their appendix, in one of the appendices, a theorem. They say that there's no lattice derivative that will satisfy Leibniz rule. Leibniz product rule is an extremely important property to have in order to prove symmetries, and that cannot be achieved by any lattice derivative. One technical aspect about their proof is the following, that when you take product of multiple fields, then the total momentum goes outside the Brillouin zone, and they fold it back into the Brillouin zone. So if you take any momentum outside the Brillouin zone, there's a unique momentum inside the Brillouin zone for which the phase will be same. And I am referring that to as folding. It's a standard thing to do in lattice. That's what they do, and they conclude that if you do that, then certainly there is no way to preserve Leibniz rule. And because of that, the theory is non-Poincare covariant and does not have desirable local properties, as were shown by Karsten and Smith, by applying this derivative in QED. So what they show is that this becomes non-renormalizable, because counter terms for doing the renormalization, those are non-local, and they don't have the right continuum limit, right local property in the continuum limit. Now, Leibniz rule was studied very extensively in the lattice literature, because that is important to have these symmetries, and that's what you need to preserve supersymmetries. And Bergner in 2010 wrote an interesting paper where he used slack derivative in order to get rid of these Fermion doubling problems, and then certain finer lattice techniques he adopted, which would take care of this Leibniz rule. However, the theory that he arrives at does satisfy supersymmetry, but not in presence of usual gauge fields, because the slack non-locality is still there because he is using slack derivative. So this is relevant for this work, as we will see that the construction that I'm going to describe actually will have a Leibniz rule and symmetries, but also not hopefully we'll get rid of non-locality. There are certain indications of that. So the new approach that I'm going to describe, I call it exact approach, is the following. So you start what we do, the usual approach is to replace continuum derivative by difference derivative, with the hope that in the h going to 0 limit, it will go back to continuum derivative. And this can be interpreted in a different way. By continuum derivative, each step actually refers to a series of calculations that we have to do in the theory. This means that in this theory, we are doing calculations by using the usual rules of continuum calculus. Here, we are using the rules of difference calculus, which is different from continuum calculus. And in the h going to 0 limit, we should go back to the continuum calculus again. So you could view this as changing the calculus rules. And for instance, h is small, difference calculus can be viewed as a correction to the continuum calculus. There is a one-to-one correspondence between the rules of the continuum calculus and difference calculus. For example, there is a Leibniz rule for the difference derivative, but that is not same as the Leibniz rule of the continuum. But the Leibniz rule of the continuum is what you need in order to preserve symmetries, not the Leibniz rule of the difference. So that additional terms will go to 0 in the h going to 0 limit. Now, suppose we are on a lattice, but we use a different derivative. That derivative satisfies all the rules of the continuum calculus. So let me call it an exact derivative, or ED in short. So if we use an exact derivative in the lattice calculation, then how does the picture change? There is no change in these steps because always we are using continuum calculus only. This means that although we are doing calculations on the lattice, each step in the calculation is exactly the same, algorithmically, exactly the same as done in the case of continuum. Okay, so therefore, these calculations are exact in that sense. And that is like that I would like to refer to as the ultra locality. It means that if you derive an equation in the continuum theory, a local equation, there will be exactly the same equation in the lattice theory site-wise, except that the continuum derivatives are replaced by the exact derivative. So then it will seem like there is no approximation done in this process. What are the steps, these steps then? So although there is no approximation in the rules of calculus, but there is an approximation in the configuration space, the space of functions on which the calculus is applying. So here we have the continuum space of function that corresponds to the continuum problem, but the space of functions corresponding to the discrete problem is different, and that space of function carries the parameter h, though the calculus does not carry that parameter. So there is an approximation in that sense. So then it would look like that the issue of continuity is not that important. Whether it's a continuum spacetime or a lattice is actually not a good question. If it were a good question, if this formulation would require that to be the right question to ask, then that would be problematic actually, because we cannot figure out objectively whether it's a continuum or not. We should not also be figure out objectively whether it's a lattice or what kind of lattice and so on. So the variables that we're using are mathematical constructions, mathematical objects. What is more important probably is how precisely we are preparing the configurations of the theory. So that's what will emerge. I'm just giving you the so this is a take-home message for this talk. This lattice theory is equivalent to a continuum theory, provided you put the right restriction on the configuration space. And that restriction has the parameter h in it, which is the scale at which the calculations are being done. And this will come out as certain mathematical results in this framework. So the question is that, is there any exact derivative like that of this kind of property? And there are two forms. One is this logarithmic form, which I discussed earlier and also discussed in the paper in 2023. Later on, I found another form, which is sine hyperbolic inverse. Both of them have infinite sum in terms of powers of difference, forward and backward difference operators. And once you have these derivatives, you can try to check whether they are really satisfying the exact calculus or not. So, for example, the power law. This power law is a continuum rule. It is not satisfied by the difference operator. But if you use either the logarithmic derivative or sine hyperbolic derivative, then you get this result. Actually, this result. So I'm referring to this. These are preliminary evidence that shows that this may be an exact derivative. These calculations are direct calculations where you directly use those expressions like logarithmic derivative or sine hyperbolic expansion. I refer to these calculations are direct calculations, but there is a more powerful indirect calculations, which is the distribution theory that I'm going to discuss later, and that predicts this relation. Once it predicts it, you should be able to verify it directly, and you try to verify it, and you end up getting an identity like this involving Stirling's Stirling numbers of first kind. For each k and l positive integer, there is an identity like this, and this for arbitrary value of k and l, proving this identity is not easy using the standard Stirling number identities that are catalogued in the literature. But if you demand this, which is a prediction of the distribution theory, then you get these identities. And I have checked them for many, many values of k and l numerically, and this relation is true. You get different sets of identities if you use sine hyperbolic derivative. So the distribution theory that I'm going to talk about next is more powerful and will result in various relations. And I will show you many of those relations it should be possible to check through direct calculations like this, all those relations that are result from the distribution theory. And each such calculation is potentially going to give you some new identities. There are certain identities involving Bernoulli numbers as well. I will not talk about these calculations in this talk because I haven't done the full job yet. There are many results, but I haven't done that fully. I think there is more to do in order to fully explore this particular direct calculations. There is this Leibniz rule which I talked about earlier. Let me skip it. If there is a question, I will answer. Now, although there are preliminary evidences, there are certain problems of these derivatives also, this exact derivative also. One problem is that it is an infinite sum of powers of difference operators. And what about it is not computable. If you give an arbitrary lattice function, then the computer will never finish the calculation, so you cannot compute it. Even if you compute it for certain special functions, there is no a priori characterization of the space of functions on which it should be computable. So that is the configuration space. What is the configuration space that is suitable for this derivative? And then there is a branch cut ambiguity. If you apply the forward difference on the Fourier mode, you get this result, and this result is completely unambiguous. But if you apply the logarithmic derivative, for example, on the Fourier mode, then the eigenvalue is log e to the ikh, and that has a logarithmic branch cut ambiguity. Each time you apply this operator, you have to choose that branch, which is this integer n. So for all calculations, you have to choose this branch independently in order to establish that in the position space, the derivative is satisfying the calculus of the continuum. So one would like to ask the question, what is the right choice for these branch cut ambiguities? So I will now describe an intuitive way out, how to interpret this problem and how to sort it out. So one way to interpret this ambiguity is that ED recognizes continuation ambiguity. The ambiguity in the calculation of ED is actually reflection of the continuation ambiguity. Or what is continuation ambiguity? This is described here. Suppose you take a lattice field psi t, then you wonder, can you write down a continuum function psi lower bar? So whenever I write a lower bar, it refers to a continuum configuration, such that continuum function calculated at xp on the lattice point, restricted on the lattice point, will give you this. So that is the restriction map R, which goes in this direction. Now there's a huge amount of ambiguity because there are infinite number of functions that you can write which will give you the same result, because between two lattice points you can do whatever you like. So the inverse map, which is the continuation, given a lattice configuration, can you find the continuum configuration, which is the continuation map, which is inverse of these two maps, restriction and continuation, are not bijections in general. So one would wonder, can we find the characterization of the space of functions such that these maps are bijections? And if these maps are bijections, then these relations will follow. So let's look at the first relation. On the left-hand side, this is the discrete derivative, nth power of the discrete derivative acting on the lattice. It's a purely lattice calculation on the left-hand side. But on the right-hand side, it's a nth power of the continuum derivative. After calculating the derivative, you restrict it to lattice. This equation must satisfy. Why? Because if you fix this ambiguity, then you are not only fixing the ambiguity for a specific function, but all possible higher derivatives of that function, because each derivative of a function is another function, and you are fixing that ambiguity. The space of functions on which the ambiguity is fixed contains all the functions and all their higher derivatives. And therefore, you have this series of relations. Each higher derivative must match on the two sides. And from there, you can argue this. Now, once these derivatives match, the inverse of the derivative, which is the integral, that should also match. And therefore, the inverse of exact derivative, which is a lattice integral, should be given by the continuum integral of the corresponding continuation psi lower bar. Okay, so these are the goals. I mean, one has to establish these relations, but this problem, there are more complications to this problem, which is the full problem, which is what now I'm going to describe. What is the full problem? The full problem, let us apply this basic idea of having an exact calculus to classical field theory. A classical field theory, you have the classical fields at a particular instant of time. This is the uncountably infinite number of degrees of freedom, which are given by certain functions on Rd. So Rd is the spatial slice. And these functions are Schwartz functions on Rd. This is a subset of smooth functions, infinity functions on Rd. And Schwartz functions satisfy rapid fall-off condition, which says that this x to the power m higher derivative acting on phi will all fall to 0 at large value of mod x. These m and these are because it's a higher dimension, so there's a multi-index, some compact notation is written. So this is what this boundary condition is used in order to prove Noether's theorem, for example. This is one ingredient, that the fluctuating fields are Schwartz function. The next ingredient is the fundamental Poisson bracket is Dirac delta function, and therefore we have distributions. So therefore you need the entire distribution theory in order to do the calculations in classical field theory. And let me just briefly tell you what distributions are, like Dirac delta function. This was done by Schwartz. So these tempered distributions are viewed as continuous linear functional on Schwartz functions, and they are viewed as a dual space to the Schwartz space. And this duality is given by this inner product. So if kappa is a tempered distribution, then it has an inner product with Schwartz field phi, and that is given by this integral. This integral must exist for all phi. And the idea is that when we know the value of this integral for all phi's in the Schwartz space, that defines kappa. Though kappa does not have a normal classical description like a function, like you can write x squared or x cubed is a function. It doesn't have a function description, but it can appear in your calculations in this inner product form. Since it does not have a function description, you cannot apply the limiting definition of a derivative of kappa, but this distribution theory allows you to define derivative of kappa in this way. It is the negative of inner product between kappa and derivative of phi. So that is how the derivative of kappa is defined. So this distribution theory enlarges the domain of applicability of the calculus, because otherwise there is no way to find out the derivative of a Dirac delta function. It's only a distribution way that you can define it. So in order to derive the calculus on the lattice also, you have to address the maximal domain, which is the distribution theory. This is a continuous linear functional, and this continuity, there are two ways of looking at it. One is the topological way, which is very abstract, and I am not qualified to do that. I understand to some extent the sequential continuity, which says that every distribution is a limit of a sequence where the elements in the sequence are Schwartz functions. So we are all familiar that the Dirac delta function can be viewed as a limit of Gaussian or other nice good functions. So it is that same statement, more mathematically rigorous statement, is that you have to construct a sequence in Schwartz space such that its limit, such that the limit of the integral exists. and all the different sequences that give you the same inner product in the limit are considered to be equivalent. So this is the structure that I will be using. I would try to realize in the context of lattice. This is done in Rn. I want to do it on a lattice. So that is the problem. What is the description of the temper distributions on Z?
Bartel, can you remind me what is a Schwartzian function?
Schwartz function is a C infinity smooth function, first of all,
Okay.
plus it satisfies rapid fall off condition. That is all. It's a smooth function, but it falls off rapidly. Like any power of x you multiply and a higher derivative you take, that is going to go to 0. So this phi, the derivative of any arbitrary high derivative of phi is going to dominate over any higher power of x at large, at the boundary, at large x. Okay. So yeah, so this will be relevant for Poincare invariance. We will see that. And because it falls off so rapidly, this the integration by parts apply. If you apply the integration by parts, the derivative, you are able to take the derivative to phi from kappa. So that's how it works. So that is the full problem that one has to address. Now the analysis starts from trying to get rid of that ambiguity, continuation ambiguity. Given a lattice function, I have to find in a unique manner the corresponding continuum function. And I'm not going to go into the detail of the argument, how one arrives at, how one fixes that unique continuum function. So let me go to the results, because the results are, I mean, it is good. It is enough to look at the results. So just like in the R, so let me take one dimension. Just like on R, I have a C infinity smooth functions. I have to define C infinity smooth functions on Z, on the lattice. And that is given by this. So C infinity smooth function on ZH is given by this direct sum, where F1 is called the fundamental field, and then Fk is the degree K field, which is a product of K fundamental fields. And the fundamental field is defined in the following way, that you take the corresponding Brillouin zone. So you have the lattice ZH, lattice with a lattice spacing H, the corresponding Brillouin zone is BH. And then you consider the space of piecewise continuous bounded functions from BH to C. That is what W is. So here are certain examples. So this is BH. It is enough to take piecewise continuous. There is no condition on derivatives of those functions, but they should be bounded. These functions can be discrete Fourier transformed on the lattice, and that's what gives you the fundamental field psi. And you take product of K such fields, that gives you degree K C infinity smooth fields. Now, because these are bounded, any higher power of K, if you multiply with psi and integrate, then that is going to be finite. And that's what is related to higher derivative of the lattice fields, of the fields on the lattice. We will come to that later, but that is the reason why it is defined this way. And what is the continuation? The continuation is the following, that in this psi hat belongs to W of BH, and you are doing a Fourier inverse transformation on ZH, meaning on the left-hand side, you get a lattice function. But instead of doing taking Fourier transformation on ZH, you could do Fourier inverse transformation on R. How would you do that? This psi hat is supported on the first Brillouin zone. You extend it to the full real line by just adding 0 values outside the Brillouin zone. Then psi hat becomes a function on R, and if you take a Fourier transformation of that function, you are going to get a function on R again. So that is psi corresponding psi lower bar. So psi lower bar and psi both come from the same functions, which is WBH, which are certain piecewise continuous bounded functions on the first Brillouin zone. In one case, you do a Fourier transform. So Fourier transformation relates the Pontryagin dual. So if you take the space to be first Brillouin zone, then the Pontryagin dual of that is the lattice. So that is how you are getting the lattice field. But if you extend this same function to full R, then the Pontryagin dual of R is R again. That is going to give you the continuum function. And this function is a unique continuation of this lattice function. So this is the description of C infinity functions. These functions will not fall off rapidly at infinity. So that is what we need for the Schwartz function on the lattice, and that is defined in this way. It is the same structure. It's a direct sum of these degree k fields, and there's a fundamental Schwartz field, which is F1. In fundamental Schwartz field, defined in exactly same manner as C infinity, except that this is a Fourier transform of C infinity BH. It is not WBH. WBH is piecewise bounded functions on the Brillouin. C infinity BH is C infinity smooth, but with compact support within the first Brillouin. Here are some profiles like that. So the function must be C infinity smooth and also have a compact support within the Brillouin. It can be anywhere within the Brillouin. So this function, for example, C infinity smooth everywhere, but right here, it is C infinity smooth everywhere in the first Brillouin, but it falls off to 0 here and here. So in this region and in this region, it is 0, exactly 0. This is going to 0 in a very strong manner because you see, this is not Taylor expandable around this point. This is a boundary point, because if you do Taylor expansion, then on one side you are supposed to get 0, that all Taylor expansion coefficients will be 0. But on the other side, it is non-zero. So it has 0 radius of convergence for a Taylor expansion. But anywhere else, it has a stellar expansion with certain radius of convergence, and it is also infinity smooth everywhere. Now, these are a subset of the WBH that I considered earlier. So these are subsets of this type of functions. And if you take these functions and then do Fourier transformation exactly the same way, in one case you do Fourier transformation, go to lattice. In the other case, you extend the function to entire R, and then Fourier transformation, do the Fourier transformation on R and get a phi lower bar, which is the unique continuation of this lattice configuration. So these are Schwartz. These functions will constitute the Schwartz space on the lattice. Once again, Schwartz space on the lattice, every Schwartz function on the lattice has a corresponding unique continuation, which is a Schwartz function in the continuum, which is this phi lower bar. So this S lower bar is basically a subset of the continuum Schwartz function, and that is uniquely connected to the lattice Schwartz functions. That is the entire structure for the Schwartz, for the field configurations. These functions are also called bump functions. So here's some picture. What is basically being done is that the bump functions is a subset of WBH, and you take these bump functions, you take this structure and do Fourier inverse transformation to lattice. You get Schwartz function as a subset of C infinity functions on the lattice. Schwartz function on the lattice, a subset of C infinity function on the lattice. Then the continuation is given by the following, that you take this structure and extend it to R by the trivial value 0 outside Brillouin. That will give you CC infinity BH to R extension, similarly W BH to R extension. You take this structure and do a Fourier inverse transformation on that, and you are going to get a continuum function, S lower bar set of Schwartz function on R, and which is a subset of C infinity functions on R, C lower bar. And the C lower bar is a subset of the full C infinity function on R, and S lower bar is a subset of the full Schwartz function in the continuum. So this is the structure we use in classical field theory. This is the structure we will use to construct lattice field theory. This picture is a little incomplete because we have this higher degree. So actual structure is here. You are taking all the k going from 1 to infinity, but the basic structure is actually the same. It is it is incorrect to say that this is S lower bar. S lower bar contains not only the, or S, not only the fundamental fields, but higher degree K fields. And that's a bigger space. So actual lattice Schwartz space contains all the higher degree field configurations. And therefore, corresponding S lower bar is also a bigger subspace of the continuum Schwartz space. So I have defined Schwartz functions. I have defined the space on which the continuation ambiguity has been fixed. And now I have to define the action of derivative and the lattice integral on those functions. And this I have talked about earlier. The derivative is given on the k degree k C infinity function on the lattice. You take the Fourier transformation, and this is the Fourier mode. And in this case, you have capital K number of momenta here. This Fourier mode by itself has ambiguities, because you can fold, as Slack did, you can fold this total momentum back into the first Brillouin, but you don't do that. Because of the prefactors of psi hat 1 to psi hat k, all these momenta are distinguishable. And therefore, that helps you to fix the logarithmic branch cut ambiguity of the discrete derivative. And the result you pick is this. For the degree k field, it is going to give you this. And that result is going to be same as the derivative of the unique continuation. And this unique continuation is nothing but the same Fourier transformation. Take the same Fourier transformation and replace xp by x, the continuum variable x. Why? Because this Fourier transformation can be interpreted as Fourier transformation on the full entire R, where all these psi hat are extended with zero values outside the Brillouin. And therefore, it's a Fourier transformation on R, not BH. And that is how psi lower bar is constructed. And this derivative of psi is same as continuum derivative of psi lower bar because of this prescription. And because of this prescription, Leibniz rule is also valid, because this is sum of the momenta. In this space now, in the C infinity ZH, on this space, the restriction and continuation maps are bijections. You can I have already told you how to define integral. It's an inverse of the derivative. Once the ambiguity of the derivative is removed, that removes the ambiguity of the integral also. And there is a prescription. Let's not go into that unless there is a question. Let me show you certain results. One result is that the lattice integral of the full C infinity lattice configuration is same as the continuum integral of the corresponding continuation, unique continuation psi lower bar. If you take psi to be a fundamental field, this C infinity has all the higher degree fields as well, but one of the subset is that fundamental field. Then this lattice integral is same as lattice summation, and it is going to be important in relating this work with the Bergner's proposal that I mentioned earlier, who use some final lattices. So that is related to this relation. I will come back to that later. Then the integral of this phase, which is the product of capital K number of phases within the Brillouin, this integral is exactly the same integral that you would get in the continuum. This follows from this first relation, and this is the usual Dirac delta function. This is responsible for the translational invariance of the field theory. And as a result, I mentioned earlier that a derivative of arbitrary product, a product of arbitrary number of C infinity fields will satisfy Leibniz rule. And if the C infinity, all the C infinity fields using certain arguments, you can show that all of them are actually falling off to zero at infinity, not rapidly, but they are going to zero anyway. And because of that, lattice integral of the discrete total derivative is always zero. Now, I have defined the space on which the field configurations on which the derivative and integral are well defined, I have to define tempered distributions on the lattice as well. And that is done by taking tempered distributions on the bump functions on the Fourier space, on the first Brillouin zone. So this is CC infinity star in BH by K. So the Schwartz functions are obtained by Fourier transformation of bump function within the first Brillouin zone. The tempered distribution, which are dual to Schwartz function in the continuum, those tempered distributions are obtained by Fourier transforming the distributions that are dual in the first Brillouin zone, which are the distributions dual to the bump function in the Brillouin zone. Okay, so you take that space, do Fourier inverse transformation, go to that goes on the lattice, that gives you the lattice distributions. And if you extend them to entire R by adding trivial zero values outside Brillouin zone, and then do a Fourier transformation, then that will give you the unique continuation of S star. Star means the dual of S. That will give you the unique continuation S star lower bar. Actually, this is a typo. This argument must be R, not because it's a continuum function, I mean distribution. So here are certain pictures which summarize whatever has been done so far. Okay, and there is a lot here, including certain theorems in the usual distribution theory. So the light shaded region is the full space of all Schwartz functions in the continuum. This is SR, is the Schwartz space in the continuum. Now you are constructing a sequence in this space, and these blobs are the elements of that sequence, such that in the limit it's a distribution. It is not a Schwartz function anymore. So it is outside that space. So it is like the distributions are like the boundary of the Schwartz function in that sense. So you have a Cauchy limit, and in the Cauchy sequence, and then the limit, the limiting value is not in the space. That's the boundary. That's the distribution, and this is the dark shaded boundary is S star of R. And then there are theorems that a Fourier transformation takes a Schwartz function to a Schwartz function. And there is another theorem which takes a distribution, which says that the Fourier transformation takes distribution to another distribution. So Fourier transformation takes a point from boundary to boundary and a point from interior to interior. Now, the lattice Schwartz functions, the unique continuation of that is S lower bar. S lower bar R is a subspace of the complete Schwartz space of the continuum. And they are obtained by Fourier inverse transformation of all these bump function spaces within the Brillouin zone. This is a k equal 0 to 1 to infinity, the entire set. So a bump function in the Brillouin zone is also a Schwartz function because it follows rapid fall-off condition. So if you take R, then the Pontryagin dual of R is another R. From position space, you are going to momentum space. So this F is taking a position space function and taking it to a momentum space function. Schwartz function in the position space is taken to a Schwartz function in the momentum space by the Fourier transformation. So the set of momentum space functions that we considered, which are the bump functions, that is a subset of the actual Schwartz space of Schwartz function in the continuum. And under Fourier transformation, it takes another region of the same space. So this picture is a bit abstract. It doesn't commit to either position space or momentum space. It is referring to R. R can be either position space or momentum space. So the bump functions are sitting here. The position space Schwartz functions are also sitting here. So this is the picture. The Fourier transformation relates to different regions of the continuum Schwartz functions. One region are these bump functions on the Brillouin zone, and the other region are the Schwartz functions on the lattice, the continuation of that. Okay. Similarly, this region has a boundary, which are the distributions corresponding to the bump function on the on the Brillouin zone, and under Fourier transformation, it will take you a boundary of these points, which is the distribution of the Schwartz function on lattice. That is what is happening. However, there's a little bit of problem here. The actual picture may be more subtle than this. And why is that so? There's a question that I don't know the answer to right now, whether S lower bar, this S lower bar, which is the which we have seen as a subset of the complete S, the complete Schwartz function on the continuum, for which we are writing the classical field theory in the continuum. That full space, the lattice Schwartz space, is a subset of that. The question is that, is it a dense subset? There is an indication that it is possible that it's a dense subset because of this structure, that it has all the summation of all values of capital K, 1 to infinity, and it may turn out, I don't have the rigorous argument for that, but it is possible that it's a dense subset. If it's a dense subset, then both this factor and this space are dense subsets of the entire space. Then then they are not separated in this way. Then this picture is naive, because dense subset means that any element in the full space, if you take any point in the full space, then you take an arbitrary small neighborhood of that point, it will contain a point in S lower bar. This is one thing, so which is not true for this picture, because I'm naively taking two different separate spaces, but it is actually S lower bar is everywhere within this space, and similarly this space, these points are also everywhere in this space. Why is it important? Because I told you that the sense in which it is an approximation is that it is approximating the configurations. So this this is the full configurations of the continuum that you consider in classical field theory in the continuum. This is the configuration space for the lattice, and it is an approximate version of that. But in this, if it is a dense subset, that means that any configuration in the continuum field theory can be approximated by a lattice configuration with arbitrary accuracy. That is what will happen if it's a dense subset. If it is not a dense subset, if this kind of a picture, then any point here cannot be any point here which exists in the continuum field theory is not cannot be realized in the lattice field theory. But if it is a dense subset, it is always possible to approximate any arbitrary continuum field configuration by a lattice field configuration with arbitrary accuracy. Okay, so now let me give you an example of the temper distribution. So the temper distribution here is the Kronecker delta for the lattice. So Kronecker delta, which is given by 1 over h delta p comma p prime. Now you introduce a continuum notation. Continuum notation is given by delta x minus x prime, where x is h times p and x prime is h times p prime. This is just a notation. Why x minus x prime? That can be justified, but right now it's a notation which can be either good or bad. It turns out to be a good notation because of this relation. One can prove this is a discrete derivative. This is not a continuum Dirac delta function. This is this one. This is this Kronecker delta function. And this derivative is the discrete exact derivative that I mentioned. One can prove this relation, and it tells that justifies the notation for the argument x minus x prime. Similarly, you can prove this identity, which is known in the continuum, where f is a function which does not have to be Schwartz. It can be fairly Schwartz. A fairly Schwartz function is as follows, that if you take f and multiply with a Schwartz function, then the product is a Schwartz function. Then f is fairly Schwartz. For example, polynomial, it's not Schwartz, but if you multiply a Schwartz function with a polynomial, that product is a Schwartz function. So polynomial is fairly Schwartz. So for all those bigger, so fairly Schwartz is bigger than Schwartz, because there are certain functions like power of x is not Schwartz, but it is included in fairly Schwartz. So this identity, it's a distributional identity, can be proved for all such fairly Schwartz functions. Now, here is this relation to direct calculation. Unlike in the case of continuum, where you have Dirac delta function, which is a genuine distribution in the sense that it is not a classical function. You cannot represent it as a classical function. That is not the case in the lattice. The Kronecker delta function is a distribution. It is not a Schwartz function. It is a distribution, but it is a genuine function. You can write numbers for it. It's a well-defined function. So you do not have to define it using the inner product. So that means whatever identities the distribution theory will give, they will have the counterpart without the inner product that continue in terms without the integral. Those identities don't exist meaningfully in the continuum because Dirac delta function is not a classical function. But those identities exist meaningfully on the lattice. And therefore, those identities can be verified directly by using the representation of the Dirac exact derivative that I mentioned. And each such verification can potentially lead to new identities of Stirling numbers or Bernoulli numbers and so on. Okay. Now, here's a relation to certain standard theorems in functional analysis. One is Pali-Wiener theorem and the other is Carlson's theorem. So Pali-Wiener theorem says that the fundamental Schwartz field that the fundamental C infinity field that I defined is real analytic. It can be extended from R to the complex plane where it will become entire. And Carlson's theorem says that for such a function, there is a uniqueness set. Uniqueness set is a subset of the domain over which the function is supposed to be defined, such that the specifying the function on the uniqueness set specifies the function everywhere, defines the function uniquely everywhere. So it turns out that according to Carlson's theorem, such a function has a uniqueness set, which is precisely the lattice. That means that if you take a function like that and specify it on the lattice only, then it uniquely determines the function everywhere in the continuum. And that is consistent with our construction because that is what we wanted to do. We wanted to have a set of lattice functions and a set of continuum functions which are in one-to-one correspondence, giving one uniquely fixes the other. That is the unique continuation that I talked about earlier. So Carlson's theorem is consistent with that. It says that the psi lower bar has same amount of information that psi has, which is a lattice field configuration. Now there is this has a strong impact for the case of quantum field theory because psi lower bar has uncountably many degrees of freedom, but psi has countably many degrees of freedom. And it is such, if you construct a field theory with psi, then that cannot have ultraviolet divergence because the momentum is cut off to first Brillouin. So that means the Schwartz functions that we have, the space of Schwartz function, continuum Schwartz functions that we have, when you do path integral over the entire Schwartz function, space of Schwartz function, it gives UV divergences. But when you do path integral on S lower bar, that is the unique continuation of the lattice Schwartz function, it is UV divergence free. And it is possible that is the dense subset of that. So how exactly this happens, how it impacts the path integral is something that is interesting to know. I have some rough understanding for the perturbative calculations, but for the non-perturbative calculations, I think it's a more serious question. Now, this construction can be generalized to higher dimension. All these statements go generalized to higher dimension. Now, one thing I should mention here, see, this uniqueness set, when you mention this, that your continuum function is fully determined by its values on the lattice, this lattice is not unique. You could give a translation to the lattice. If you give a translation, so the uniqueness set itself is not unique. You can have infinite number of uniqueness set which are related by translations in 1D. And all of them are equally good to specify the particular function psi lower bar x. And that is why writing a field theory on the lattice using psi p can incorporate translational invariance. And the higher D version of that is the Euclidean group of transformation. So all the Schwartz functions on the lattice that I have considered and take the corresponding continuation, that is phi lower bar, then that phi lower bar can be uniquely fixed by specifying the function on one lattice or any Euclidean group transformed lattice, that is x prime, x or x prime. And there is a momentum space version of that, which comes very handy in interpreting Feynman, perturbative Feynman diagrams. And this is as follows: that we take the Brillouin zone. The Brillouin zone, we have usual way of defining, is just a hypercube. But if you take the diagonal of that hypercube, that vector, d-dimensional vector, uniquely fixes the hypercube. And this diagonal can be rotated. It will rotate the hypercube. So you could define Brillouin zone as the hypercube defined by a specific diagonal. And under this transformation, that diagonal rotates. And what one can argue is that if you take bump functions on omega and then Fourier inverse transformation, whatever space you get the same space if you do the Fourier inverse transformation on the bump functions on the rotated hypercube. You will get the same space. So the Schwartz function, this means that the Schwartz function that I have defined is closed under Poincaré transformation. So I have defined Poincaré, it's like a Euclidean group of transformation because I have taken a spatial slice. You could do D+1 dimensional Euclidean space, or the way I have done here, the spatial slice times continuous time. This is a basic argument, but you can generalize it to that entire thing, which is a foliation D+1 dimensional space, which is foliated by the D-dimensional subspaces where you have the lattice. And this you can just construct the argument there as well. So that entire space of the functions that are appearing constructing the theory, field theory, is closed under full Poincaré transformation. Now, application. So you take a scalar field with arbitrary potential, and here are the Poincaré charges for the lattice. So these are lattice expressions, but written in continuum notation. It's a lattice integral. You see this pi and phi. Pi is phi dot. So if phi is in Schwartz, phi dot is also in Schwartz, and these are Schwartz fields. But look at L mu nu. L mu nu has this lambda, which is the Lorentz deformation vector. Deformation vector field, and that is linear in X. So this is not Schwartz. So Lorentz deformation vector is not a Schwartz function, and it's a distribution because it's a polynomial. It's the power of x to the power 1. So this L mu nu is a distribution inner product. And this is important because for non-compact spaces, when I did this work for the string worldsheet, which is a circle, for the circle, Schwartz space is simpler. It's just a smooth functions, periodic functions. All the symmetry deformations are vector fields, which are also periodic. And this issue, that's much simpler problem. But when you go to Poincaré, when you try to construct Poincaré invariant field theory on the lattice, then you have to incorporate vector fields that are not Schwartz. And to incorporate that, you need this distribution structure. And then you can derive the Poincaré algebra for the lattice. This is the result. Now, as I said, that the fundamental integral, lattice integral of the fundamental field can be written as a summation. If you take higher degree fields, not the fundamental field, a higher degree field, psi k, it can be viewed as a fundamental field on a lattice of spacing h by k. And therefore, this relation will be true with h being replaced by h by k. And that is what Bergman did in some sense. So if you write a theory where higher powers of fields are present, you just write a finer lattice expression, which are equivalent to that lattice integral. And that is what you would get this Bergner's expression. So that finer lattice technique is an overlap between this and what Bergner did at that time. But the other background stuff that I said that makes the theory ultra-local, that is not true for Bergner's theory. Bergner's theory is still non-local because he's treating derivative in a slack manner. The momentum space of the lattice theory will be the momentum space theory corresponding to the lattice theory is the same as the continuum theory, but with the sharp momentum cutoff at the first Brillouin zone. So we always thought that the lattice theory and the momentum cutoff theory, which is momentum cutoff has been initially considered as a UV regulator. So momentum cutoff theory and lattice theory should be somewhat related, but the usual construction of the lattice theory and momentum cutoff theory, the relation between them is very complicated, and the relation is established only in the continuum limit. Here, what it shows is that the momentum cutoff theory has a covariant interpretation on the position space given by this particular lattice theory. Momentum cutoff theory was not considered seriously because it interfered with gauge invariance. The reason is that in momentum space, a gauge mode under a gauge transformation, a gauge mode within the first Brillouin zone will go outside the first Brillouin zone. But because of the precise definition of the configuration space in terms of bump functions, this is not going to happen. So this momentum cutoff theory is the same that was considered earlier, but with configuration space restricted in this particular way, where the configurations are all bump function within the first Brillouin zone. That was not considered earlier. That is the difference. And that difference solves the interference of this cutoff with gauge transformation, gauge invariance. This construction, as I just said, can be realized using summation, which is less abstract and is computable. And according to Bergman's paper, one can do simulation on that. I don't understand that because I don't understand simulation yet. So, but this is a statement that I'm borrowing from Bergner 2010. If you do lattice path integral over the lattice Schwartz space, that is same as continuum path integral over the continuation of the lattice Schwartz space, that is S lower bar on RD. And you can actually formulate path integral quantization of the lattice theory and argue this. And then that it imply that the endpoint Green's function in the lattice is just the restriction of the endpoint Green's function of the continuum theory, where the path integral is done on S lower bar. So that is G lower bar. That is not the usual continuum theory. In the usual continuum theory, you do path integral over SRD. That is the total Schwartz space. But this is a restricted, S lower bar is a subset of that. If you do path integral over that, then that defines G lower bar. And then if you take that Green's function and restrict, that gives you a Green's function on the lattice. And using this result, you can calculate Poincare invariant quantum effective action at a finite h. And these arguments are also expected to go through for gauge theory, which I haven't done explicitly so far. There is a generalization of this construction to curved spacetime, which are globally hyperbolic and conformally flat Cauchy slices. So it's a globally hyperbolic space, and the Cauchy slice, the spatial slice, should be conformally flat, and string worldsheet is an example of that. And that is what 2023 paper was done. And their two-dimensional Virasoro algebra and target space isometry algebra were derived using the lattice theory. Lattice, I mean, that is the string bits. I mean, this S1 is discretized to n number of points. So I'm done, and I'll just end with some remarks on the future. Yeah, I have a lot of time, actually. No, I don't know. How much time do I have?
Minus
10.
something. Minus 10 seconds. Minus 10 minutes.
Okay. So this is the last slide. So the question I already mentioned, that the density of S lower bar within S, whether it's a dense subspace or not, then within the continuum hypothesis scenario, that means you take continuum limit, but taking H as a UV cutoff, then you can do concrete perturbative calculations, and especially for gauge theories. And then what is the precise and consistent formulation of QFT with a finite H, where H is interpreted as a scale? How do I formulate renormalization group? How do I match results with phenomenology? And is it possible to do axiomatic QFT also for a finite H? in the topological classical solutions, typically those solutions are not in the Schwartz space, but they can be most likely viewed as distributions. But that is something that one has to look at, whether the topological solutions like insentence and all can be realized here as well. And of course, the non-perturbative calculations, which I do not understand, because one has to study the path integral on these bump functions. That is where the question boils down to for the quantum field theoretic context. And for the classical field theory, classical equation or the differential equation context, is there any numerical methods that uses this exact calculus the way I described? Will there be a corresponding numerical recipes for that? That is another question. I end here. Thank you for your attention.
Hey, any questions? So I have a question. I didn't understand everything you said, but one significant point seems to be that you have a way of having exact gauge invariance with momentum space regulator. Is that right?
Yeah.
So it can be checked that the ward identities are exactly satisfied.
Yeah, those things have to be, I think, checked. I hope this will all go through, but I haven't done that yet. All this. For the scalar field, I have gone to the explicit things, but it is a momentum cutoff, but still has a gauge invariance because the gauge field configurations are all bump functions. If you take that restriction, then these are all okay. There is no interference.
I see. So I think a check of ward identities should be useful, right?
Yeah, a lot of perturbative calculations should be done, I think.
Right.
First.
Right, yeah.
And RG.
Yeah. More questions?
Could I, let me turn on my video. So with this formulation, so where you have this, exact derivative formulation, but with this scale, the H put into the thing, in that formulation, corresponding to the exact derivative, is there then a exact translation invariance?
Yeah. There's an infinitesimal translation and Lorentz invariance. Full Poincare invariance.
Right.
Yeah, the algebra I showed. Yeah, this is the algebra. I mean, you can construct this, the charges explicitly. This is lattice integral. These are all lattice derivatives.
But in some sense, because of this restriction on your configuration space, there's no object in the theory. For instance, let's say you're trying to use it to compute correlators or something like this. There's just no way of describing there's no configuration corresponding to insertions closer than this separation H. Is that?
That is true. That is true. But you can, because of this result, the left hand side is the Green's function on the lattice. Their x's are on the lattice. But on the right hand side, this G lower bar, it's in the continuum. These x lower bars are continuous, continuum variables. Because the lattice configuration every lattice configuration has a unique continuation.
Right.
And that space is S lower bar. That is a subspace of the full continuum Schwartz space. So you are doing path integral on the subspace only.
Maybe here's a different way of asking the question. I'm not quite sure I'm really getting it, but if you do this unique continuation to the continuum of the Green's functions, can you characterize what the singularities will look like as I continue to x1 approaching x1 underscore approaching x2 underscore?
Yeah, I mean, Yeah, so after continuation, I have to check it explicitly. But you know this formulation by Stickelberg, Peterman, very initial stage of development of QFT, they said that the large momentum, the UV divergences can be viewed from the position space as Dirac delta function divergences. And that is how they actually formulated. So here all those are going to...
I wasn't so much interested in the contact term as in how the Green's function obeys. You know, is it power law or what behavior?
Yeah, that I have.
Or
So
small separations of the.
Yeah, there is no high momentum modes, right? So on the
Right.
lattice, I know, but
Yeah.
okay, I know. See this. Okay, so you could ask this question: the Dirac delta function of the continuum becomes Kronecker delta on the lattice.
Yeah.
Now I have defined this unique continuation to the continuum. So you could
Right.
ask, what is the continuation of Dirac Kronecker delta to the continuum? That is not Dirac delta. That's an oscillatory function actually. That's a smooth function, which becomes Kronecker delta only on the lattice points. In between lattice points, that's a smooth function. So it will be written probably in terms of that, because on the lattice, this is any Dirac delta function in the continuum will be replaced by Kronecker delta. Now what you are doing is basically replacing the discrete points by some continuum points. So those are like continuation of that Kronecker delta. So those are some smooth functions.
Right.
And from momentum space point of view, there is no high momentum mode because momentum is cut off to the Brillouin zone.
Interesting. So this, if you had just handed over to me these continuum Green's functions that you found by continuation from the lattice model with spacing h, I would be able to detect the lattice spacing, so to speak, as some kind of smooth Poincaré invariant kind of short distance regulator or smoothing of this behavior.
That is true, because the configuration space, this S lower bar has the information of H.
Yeah.
Or the Brillouin zone has the information of H. So if you go to the momentum space language, the integration limit has the dependence on H. I've done some few perturbative calculations. It turns out to be same as the usual, say, Feynman diagram calculations with a momentum cutoff, which has certain divergence behavior, etc. Those will come as usual. But the point is that now usually one says that that is not Lorentz invariant, because so you don't calculate Lorentz transformation of a Feynman diagram. Like Feynman diagram is just a number. But there is a formulation how to look at that by transforming, giving a Lorentz transformation. And there, this diagonal of a hypercube, that picture helps.
Okay, maybe one last question. Sorry, because I know it's going late, but so in this continuum, is there an analog of a locally conserved stress tensor in the continuum description? In other words, maybe that's not a well-posed.
Well, I mean, so usually in continuum field theory, what you do is to couple it to G mu nu and then take derivative and define it. But then you can fix G mu nu to beta mu nu. So that certainly gives certain some expression. You can certainly calculate that and it will be consistent. The algebra will be consistent. Somewhat like that is done, was done for the string worldsheet, right? Because there is a T, basically Virasoro algebra is basically TTOP.
Sure.
So in the position space, it has the same expression on the right-hand side in terms of the derivative of delta functions and so on. So in some form, they will look exactly same. but they are not. I mean, these are not Dirac delta. These are Kronecker delta functions. In some notation, they are same, and the operations are follow the same rules, but quantitatively they are different. So there will be no divergence.
I guess my intuition tells me that even though you've found a way of preserving the global Poincare, global continuous Poincare symmetry, that this theory with this kind of cutoff H wouldn't have a locally conserved stress energy tensor. But but I guess I'm asking that as a question, whether
So far,
something that goes wrong with the local conservation.
Okay.
When you try to do this continuum, whatever you call it.
Local conservation by covariant conservation of T mu nu, D mu, T mu nu equal to 0. Yeah. So in a general field theory coupled to G mu nu, you can prove that, right, in that field theory. Right. Now, you take that background to be that globally hyperbolic with Cauchy slice being conformally flat. If you restrict to that background, then whatever result the continuum theory predicts, it will give the same result, I suppose, because the same calculation, my calculus rules are same. Mm-hmm. Now, I don't know the general thing. I think there should be some general argument, and it should be possible to generalize it to arbitrary background. In using, I mean, at least how much useful, I don't know that is going to be, but I think there should be a formulation in terms of like the point is that where you write, you are basically choosing, you are restricting the configurations in such a way that have the uniqueness set. And that uniqueness, choice of the uniqueness set is non-unique. So you could try to formulate, I haven't done that yet, using Riemann normal coordinate and map everything to the tangent space. There's a complicated transformation, but on the tangent space, you can take the lattice on the tangent space, basically the uniqueness set points. And then you revert, then you do the inverse coordinate transformation and see what you get, whether it is useful or not, and so on. But certainly, the basic point, I think, is that the configurations you are choosing them in a restricted manner such that there are countable degrees of freedom.
Right.
And that is the only issue in defining. I think the main issue in defining quantum field theory measure, I think, the UV divergence issue. I mean, the UV divergence is appearing because it's uncountably infinite.
Mm-hmm. Okay, well, interesting.
Yeah, we sort of went beyond time.
Sorry for the late.
So maybe I think for further question, just email Partho.
Sure.
That's certainly fine. Yeah. Thank you.
Okay.
Okay.
Thank you so much. Thank you all.
Very much, Partho.
Bye.
Thank you.
Thank you.
Bye-bye.
Thank you.
Bye.